innovative and dynamic learning, getting students towards new normal. You are watching Telescuela of the Division of Agusan del Sur.
Good day, our dear grade 12 learners. I hope you are well and safe amidst the pandemic. Welcome to the last episode of our three-part lesson in Physical Science for Quarter 3, Week 2. So, find a comfortable spot in front of your television and be ready as we explore once again the wonderful world of science. Hi, I am Teacher Jeffrey. I will guide you through this 20-minute lesson on polarity. If you are ready, then let's get started. In our previous lesson, you have learned about molecular shapes according to the valence shell electron pair repulsion, or VSEPR theory. Recall that we can only draw the shapes if we know its loose knot structure. Now, I want to see if you can still identify shapes of the molecules that I will be showing you. Number 1. What is the molecular shape of water, or H2O? Very good! It is bent. Number 2. What is the molecular shape of boron trihydride, or BH3? That's right, it is trigonal planar. Number 3. What is the molecular shape of chlorine, or Cl2? Correct! It is linear. Well done! I am glad that you are still familiar with the common molecular shapes. Aside from linear, bent, trigonal planar, we also have trigonal pyramidal and tetrahedral. This time, I have here common substances that can also be found in your homes. I have here water, cooking oil, and dishwashing liquid. Now, answer my questions based on your previous experience. Will water and cooking oil mix or not? How about water and dishwashing liquid? How about cooking oil and dishwashing liquid? I can almost hear your answers. Whether the pairs that I have shown you will mix or not, that depends on one of their properties. That will be the topic of our discussion today, polarity of molecules. For this lesson, you are expected to determine whether a molecule is polar or non-polar, given its structure or shape. Let us start with a short experiment. If you can recall from our previous episode, I have given you a list of common household substances that you can prepare at home to conduct a simple activity for today's lesson with me. Don't forget to ask assistance from your adult companions in handling the substances to avoid accidents, especially gasoline, for this is hazardous. In disposing cooking oil and gasoline, mix it first with dishwashing liquid before draining it into the sink. Be sure that you have now the following substances and materials: water, cooking oil, gasoline, dishwashing liquid, test tubes or beaker, or any small-sized container available in your homes, stirring rod, or any piece of wooden stick, and your paper for jotting down your observation. You can do the activity by following the steps that I will be showing you. Then, observe whether each pair of substances would mix or not. Do not forget to always wash and dry your stick if you are going to reuse it for another substances. Write your observations Can you see what happened when you stir it? They mixed quite well too. Why do these substances behave differently when paired with other substances? These behaviors can be explained by a molecular property called polarity. Remember, it tells whether there is equal or unequal distribution of electrons among the atoms in a molecule. A molecule is nonpolar when there is equal or symmetrical distribution of electrons. On the other hand, a molecule is polar when there is unequal or asymmetrical distribution of electrons. Unequal distribution of electrons happens when one of the atoms are attracting the electrons more strongly towards themselves. It creates a dipole moment, or separation of positive and negative charge. We use these symbols for labeling the partial positive and partial negative sides. We also use arrow that points from the partially positive to the partially negative side. Whether a molecule is polar or nonpolar greatly depends on its molecular structure or shape. Let us start with a diatomic molecule of oxygen. This is its Lewis dot structure. Can you identify what is the molecular shape? Correct. This molecule is linear shaped. Since both are the same type of atom, they pull the electrons equally on either sides, canceling out their dipole moment. A balance or symmetry of charges can be observed, and thus, it is a nonpolar molecule. Now, take a look at this another molecule, hydrochloric acid or HCl. We commonly call it at home as muriatic acid. This is its Lewis dot structure. Now, can you tell me its molecular shape? That's right, it is also linear shaped. Notice that the hydrogen atom bonded with the chlorine atom by sharing electrons here. However, chlorine still has 3 lone pairs. They are pairs of electrons that were not bonded with other atoms. So, we can say that electrons are quite more concentrated on this side. Thus, we label it as partially negative. The other side becomes partially positive. This creates a dipole moment. Since there is a symmetry here, hydrochloric acid is a polar molecule. Since there is asymmetry here, hydrochloric acid is a polar molecule. You see that although both are linear, oxygen molecule is nonpolar, while hydrochloric acid is polar. This time, let us take another example, water or H2O. This is its Lewis dot structure. Can you recall what is its molecular shape? That's right, we classify it as bent-shaped. Notice that hydrogen atoms have both bonded with 2 of oxygen's electrons. However, there are still 2 lone pairs out here. We can then say that on this side is where electrons seem to be more concentrated. Thus, this side is partially negative, while this side is partially positive. A dipole moment is created. Therefore, water is a polar molecule. The presence of lone pairs of electrons in one side of a molecule creates dipole moment. Remember, all bent-shaped molecules are polar molecules. We have another molecule. This is boron trihydride or BH3. Its Lewis dot structure looks like this. Can you then determine its molecular shape? You're right, this molecule is trigonal planar. The hydrogen atoms are arranged symmetrically around boron. The dipole moment of each of the 3 boron-hydrogen bonds cancels out each other. Thus, boron trihydride is a nonpolar molecule. Let us take, for example, another molecule, formaldehyde. This substance is used to preserve biological specimens. This is its Lewis dot structure. Can you tell what is its molecular shape? That's good. This is also trigonal planar. The central atom carbon bonded with the two hydrogen atoms and an oxygen atom. However, notice that on this side, there are still two lone pairs. We can say that on this side is where electrons are more concentrated. Thus, this side is partially negative and this side is partially positive. A dipole moment is present, so formaldehyde is a polar molecule. Atoms around the central atom affects the overall polarity of a molecule, even though they are arranged symmetrically. In our examples, both molecules are trigonal planar, but boron trihydride is nonpolar, while formaldehyde is polar. Let us proceed with ammonia, or NH3. Its Lewis dot structure looks like this. Can you identify what is its molecular shape? Correct! It is trigonal pyramidal. The three hydrogen atoms bonded with the nitrogen atom at the center. Notice that there is still a lone pair left. We could say that this side is where electrons are more concentrated. Thus, we can label this as partially negative and this as partially positive. There is asymmetry of charges, so a dipole moment is present. Therefore, ammonia is a polar molecule. The presence of lone pairs of electrons in one side of a molecule creates a dipole moment. Remember, all molecules that are trigonal planar are polar molecules. For our next example, consider this molecule methane, or CH4. This is how we draw its Lewis dot structure. Then, what is its molecular shape? Correct. Methane's shape is tetrahedral. Notice that hydrogen atoms are arranged symmetrically around carbon. There is no lone pair in its structure. The dipole moment of each of the four hydrogen-carbon bonds cancels out each other. Therefore, methane is a nonpolar molecule. Lastly, study this molecule fluoromethane, or CH3F. This is its Lewis dot structure. What is its molecular shape? Correct. This is also a tetrahedral-shaped molecule. The central atom, carbon, has bonds with the three molecules of hydrogen and one atom of fluorine. Can you see a concentration of electrons? That's right, electrons tend to be more concentrated near fluorine. This is partially negative, while this one is partially positive. So a dipole moment is present. Thus, fluoromethane is a polar molecule. Atoms attached to the central atom affects the overall polarity of a molecule, even though they are arranged symmetrically. In our examples, both molecules are tetrahedral, but methane is nonpolar, while fluoromethane is polar. Now, it's time for you to identify the polarity of the molecules on your own. Are you ready? Number 1. Silicon tetrahydride, or SiH4. Is it polar or nonpolar? Correct! Since all of the dipole moments of silicon-hydrogen bond cancel each other, symmetry in its shape is evident. Therefore, it is a nonpolar molecule. Number 2. Phosphorus trihydride, or PH3. Is it polar or nonpolar? You are right. As you have noticed, this side of the molecule is partially negative due to the presence of a lone pair here, while this becomes partially positive. Therefore, phosphorus trihydride is a polar molecule. Number 3. Ozone, or O3. Is it polar or nonpolar? You're correct. Looking at its structure, ozone has a dipole moment. This side is partially negative, while this side is partially positive. Therefore, ozone is a polar molecule. Number 4. Carbon dioxide or CO2. Is it polar or non-polar? That's nice! As you notice, the two oxygen atoms attract electrons equally. Both sides are partially negative, and thus their dipole moments cancel each other. This makes carbon dioxide a non-polar molecule. You have done a great job in identifying whether those molecules are polar or non-polar. But wait, why is knowing the polarity of molecule important? One phenomenon that can be explained by polarity is whether or not one substance dissolves in or can be mixed with another substance. In your activity, recall that water and cooking oil did not mix. That is because water molecules are polar, while molecules in cooking oil are non-polar. Water and dishwashing liquid quite mixed. Water molecules are polar, while molecules of dishwashing liquid are also polar. Cooking oil and dishwashing liquid quite mixed too. Molecules in cooking oil are non-polar, while molecules in dishwashing liquid are also non-polar. So you see, polar dissolves polar and non-polar dissolves non-polar. Simply put, like dissolves like. Can you see something unusual about dishwashing liquid? Good observation! Soaps in general can both mix with a polar molecule and a non-polar molecule. Soaps have both a polar or water-loving tail and non-polar or a water-fearing tail. An example of a molecule that can be found in its polar tail is sodium hydroxide. So, when we wash our dirty and greasy hands, we wet first our hands. This helps remove dirt that are polar in nature that can bond with water. Next, we put soap on our hands. The non-polar tail of the soap bond with the grease or oil. And what's the next step? That's right, we rinse with water. The polar molecules of water bond with the polar tail of the soap. Voila! We can be sure that our hands are now clean. To sum up, the polarity of molecules depends heavily on its structure or shape. Since their charges are asymmetrically arranged, all molecules that are bent and trigonal pyramidal are polar. On the other hand, molecules that are linear, trigonal planar, or tetrahedral can be classified as polar or non-polar, depending on the atoms attached to the central atom and the presence of lone pairs. It's quiz time! Get your papers ready because I am going to show you names of some molecules and you are going to identify whether they are polar or non-polar. I will give you time to copy the items and you can answer later. Number 1. Diatomic fluorine. Number 2. Nitrogen triiodide. Number 3. Boron trifluoride. Number 4. Fluoromethane. Number 5. Hydrogen cyanide. There you have it! Science is truly amazing. I hope you had fun in learning about polarity as much as I do. I will definitely see you again in our next lesson. I am your teacher, Jeffrey. Have a great and a safe day.